Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I want to talk to you about climate change because it's interesting and because it's important. And I do think the skills that you have in this room could be helpful to that important topic. I'm going to aim to tell you about 3 or 5 things, depending how time goes. So the first 3 are interesting, and the second 2 are the important bit. So I'm going to talk about historical climate change first, going back hundreds of thousands of years. First, let's go to Antarctica, and you drill down through the Antarctic ice sheet. You can see stripes there in that photograph. Those are years. Each stripe is caused by a year of snowfall. And as you drill down, you can measure the heavy oxygen depletion and the heavy hydrogen depletion as a function of depth. And what you see is it goes wobbling up and down and up and down and up and down. And those wobbles are years. And why does it wobble up and down? Well, because the temperature at which the snow is falling onto Antarctica has a slight effect on the isotope ratio of the oxygen and your deuterium, thanks to physics. And so you're getting a temperature signal in the water. You take the water out of this ice core and you can deduce an indication of what the temperature was. Okay, so we've got a temperature signal. And you can drill further down. The top graph is going back 50 years, wobble, 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 looking at the deuterium. And then the bottom 2 graphs are looking at deuterium and oxygen and seeing what the temperature did for the last 40,000 years. And what you see is, something interesting happened there. There was a big change of temperature. It was much colder back here 15,000 years ago because that was the last ice age. Okay. And you keep on drilling down and down in another location, and you get 800,000 years of the temperature, deuterium, going up and down. So I'm just showing you the deuterium deficit. You can turn it into a temperature if you want. And you can also measure in the same ice the carbon dioxide concentration in the bubbles of air that are trapped in the ice. And that's shown in the red graph. And people have often noted how these are quite strongly correlated with each other. And I've just scaled and slid them on top of each other arbitrarily to make that bottom picture, which is the deuterium and the CO2 graphs on top of each other. Now, why am I showing this? Well, Al Gore showed it in his movie. And people who don't like the politics of climate change action try and criticize everything that Al Gore and climate scientists say. And I think they have the impression that what Al Gore was saying was, ooh, look at how the CO2 changed and the temperature changed. And maybe they thought Al Gore was saying that there was causation, that the CO2 caused the temperature. And Al Gore certainly was saying that if you put extra CO2 in an atmosphere, you'll get a bigger greenhouse effect, and that will give you warming. That is a true mechanistic model. The physics says that that will happen. But was he saying that these graphs are illustrating that? I don't think he was, but maybe people misunderstood and thought he was saying that. So when they attack Al Gore, one thing they say is, oh, but if we can show that the CO2 lags the temperature, then that will disprove this whole Al Gore nonsense. All right? So you look at these graphs and you say, is the temperature lagging the CO2, or is the CO2 lagging the temperature? Now, you know that that's not a sensible question to be asking, because actually what you're looking at is a very complicated dynamical system with CO2 concentration and global temperature being variables among billions of variables that are all affecting each other in a complicated way. And we're just looking at the natural evolution of this system as it does its own chaotic thing and as it's influenced by external forces as well. But let's look at this lagging and leading thing anyway, just to see what we make of it. And my suggestion to you is that when you stare at these graphs, it's got a sort of time asymmetry that the coming out of an ice age, this is the most recent coming out of an ice age. Here's the one before. Here's the one before that. Well, maybe this was one as well. The coming outs are quite rapid and abrupt and steep. And I'd suggest that the change in temperature in CO2, as I've shown them here, they're sort of synchronous. You can't tell which is lagging or leading. The going back into ice ages, coming down these slopes here, seems to have a very different mechanism and to have a different time scale to it. Okay? And it's conceivable that in a few cases you could say, oh, look, the CO2 is lagging the temperature. Ha-ha. Yeah, so the blue is the temperature, and the CO2 is lagging in this particular going down. Okay, well, who cares? There's a mechanism for going back into ice ages, and maybe CO2 lags temperature in that. But what we're doing at the moment is shoving a load of CO2 into the system, and the exits from ice ages seem to involve a mechanism where maybe there's some sort of positive feedback between CO2 and temperature, and maybe other things all reinforcing each other, so you get CO2 going up, temperature going up, giving you more CO2, giving you more temperature. Okay, so I suggest that there's different mechanisms on the way up and the way down, and indeed that's what the climate scientists say too. And neither of those mechanisms is the little causal thing that we just talked about. So it is a complicated dynamical system. And the abrupt climate change happens during the destruction of ice sheets. The sort of things that are going on in this dynamical system are, first, there's a water vapor feedback. Water vapor is a very important greenhouse gas. So when you put extra CO2 in, then you'll get warming, which gives you more water vapor. The warmer atmosphere can hold more water vapor, so you get more greenhouse effect. So there's a positive feedback there. It's not an unstable feedback, but there is a positive feedback of some size. Other interesting feedbacks are if you start melting your ice sheets, then you get pools of water and bits of open ocean, which have a much lower albedo. They absorb more sunshine, and getting more radiation absorbed from the sun means more warming. If you warm up your ocean, it can hold less CO2, thanks to Henry's law. So you get the CO2 being outgassed, which gives you more warming. So there's a potential positive feedback there. And then another very complicated thing is if you have very large-scale melting of ice sheets, that dumps fresh water into the ocean, and that can then have a significant effect on ocean circulation. So these are the sort of complicated things that are actually going on during that entire time series. There's a paper in Nature. Let's maybe zoom into this a little bit. There's a Nature paper, fairly recent, that's looked in more detail at what happened in the last glaciation, because what the data from Antarctica shows, which is the red is Antarctica temperature, and the yellow dots are the atmospheric CO2 in Antarctica. What this paper shows is there's a difference between the Antarctica temperature and the global temperature. So they went and got surrogates, temperature surrogates all over the world. And the blue line shows what the global temperature, average temperature, was doing during that last deglaciation. And what you can see is once it gets going, the CO2 globally, which you can measure in Antarctica because it's well mixed, in yellow, is actually leading the temperature, the global temperature. But Antarctic temperature is a bit different from global temperature because one thing that's going on is it's one of these melting ice sheets changes the ocean circulation things, and they've got a name for it. They call it the bipolar seesaw. Maybe I don't need to explain the story in full detail, but the bottom line here is the last deglaciation has been measured accurately, and during that last deglaciation, during most of it, the rise in CO2 did precede the rise in temperature. And so, but what's the mechanism that's driving all of these ice ages? something I had heard about decades ago is the idea of Milankovitch cycles, that, oh, it's something to do with changes in the orbit of the Earth and the precession of the Earth's axis. But I hadn't actually heard the details of how that works. So I'd seen pictures of changing orbits and graphs of changes in obliquity and eccentricity and so forth, but it always seemed a bit dissatisfying to me that the evidence for the Earth's orbit causing the Ice Age timings, it seemed to be a bit fuzzy. There wasn't a clear mechanism because I'd heard about papers where they did Fourier analysis, so they would Fourier analyze data on global ice, the global ice volume, and then look at the power spectrum and say, oh, look at all those peaks that correspond to orbital frequency. So here's one such paper where they've taken the astronomy in the solid line, so the as the orbit of the Earth changes and the precession, as the axis of the Earth precesses, you can look at what happens to the summer installation. How hot is summer in the northern hemisphere? And there are slight variations in that, and you can Fourier analyze that time series, and that gives you the black solid line. And then you look at the geology. You drill down for hundreds of thousands of years and make geological measurements of oxygen isotope ratios, which is a proxy for global ice volume, and you Fourier analyze that, and you get the dotted line, and then you say, oh, look at all these things that line up. And so it must be an astronomical cause that gives you the ice ages. And that isn't really a mechanism. It's just, well, it's quite strong evidence, but I've always wanted to know a mechanism. And having hung out with climate scientists for a bit, I now have picked up that there is actually a mechanism, and it's quite interesting. So here's two Nature papers that are both quite recent, which give more detail to this. The reason it's sort of dissatisfying is the periods just don't actually agree. All of the big spikes in this thing, the precession story, it's 22,000 years, 24,000 years, 19,000 years, and then obliquity, 41,000 years. That's where all the big things are in this diagram. But what's the periodicity of ice ages? 100,000 years. 100,000 years. It's about every 100,000 years, roughly, that you get an ice age. So it always struck me that there was a difficulty that these spikes weren't actually agreeing with the main frequency. And there's an explanation for that. So first, there's a sort of empirical paper saying, here's a deterministic model where you can take the sunshine curve and turn it into a predictor of ice volume. And they show that with this red jagged line. So they've come up with a threshold idea that you take the solar curve. When it hits a particular threshold, then that gives you deglaciation. And that does quite a good job, I'd say, of reproducing this zigzag line of ice volume. It gets most of the deglaciations right. Doesn't get this one. Doesn't get these two here. But it's sort of suggestive that they're onto something. Now, what's the actual mechanism that they believe is going on here? Where does this 100,000-year timescale come from? Well, here's my understanding of the mechanism that the climate scientists think is going on and that is giving the timescale. Imagine we start out in a state where you've got a load of ice in the northern hemisphere, and it's cold and it's snowing and the ice is building up. Okay, so you go from here to here and the ice is built up. Now, on a much longer time scale, that enormous weight of ice, a mile deep or so, is typical thickness of an ice cap, crushes the ground down, so the ground elastically responds. And you squish the ground down with your ice until the ground is below sea level, and then the ocean can come in the summer and go gobble, 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 and eat your glacier from underneath, and you get very rapid loss of your ice cap, rapid on a geological timescale. So gobble, 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 the ice disappears, and then the ground recovers, and you have this rebound of the ground, which is still happening in many places in the world now after the last ice age. So there's a model, and this is a cycle. This is a spontaneous cyclic phenomenon that will just happen by itself. It's got its own time scale, and it's to do with the time scale of how long it takes for the ice to build up and for the ground to squish down. So the story here is this thing would have been going on and would give you an approximately 100,000 year period. But then along comes the sunshine and kicks it. And so the phase of the solar signal, the orbital signal, makes the deglaciation happen in a way that gives you, they call it pacing. It determines the timing of the deglaciation. And that's why you get the signal coming through in the Fourier analysis. Okay, so the second Nature paper I mentioned has a much more detailed physical model of this whole process. So they've modeled ice caps in different locations in the world, and they've made a model which shows a natural cyclic behavior. It shows hysteresis. If you had a world with fixed CO2 concentrations and fixed sunshine, fixed seasons, then it would just go round and round this blue and red loop. But then what the changes in the Earth's orbital parameters are doing is moving us around on this diagram. So you can read the paper if you're interested in more details. This is a model that can actually predict the timings of the ice ages. So what's the message so far? The message is the climate is a twitchy, complex system full of chaotic natural variability and potential instability. So very twitchy, very sensitive. So mess with it at your peril, I think, is a reasonable thing to say. It's very complicated and maybe quite hard to predict what will happen, but given how sensitive it is, it's quite credible that if you mess with it, you're going to get some radical changes. So, wouldn't it be handy if we could just do some experiments on a planet and see what actually happens when you do this other thing, instead of letting it naturally just do its own thing, which doesn't tell you what will happen when we do this new thing that humanity is doing. We put in tons of CO2 into the atmosphere. It would be nice to know what happens, because that's quite different from business as usual in the natural system. Wouldn't it be handy if we could look at the results of a mega carbon release experiment? Well, the wonderful thing is nature has occasionally, very rarely, done this for us. So the third thing I want to tell you about is the Paleocene-Eocene thermal maximum. And this happened 55 million years ago. If you look, you drill down now in rocks and look at temperature surrogates in the rocks, again using isotope measurements, you can see the history of the temperature of the planet. It was a completely different planet 55 million years ago, much warmer, it was sort of dinosaur-like conditions. So the dinosaurs had been wiped out in 66 million years ago. So it was a warm and different planet, but there's this spike here in temperature at 55 million years. And this has recently been analyzed in far more detail, again, using Fourier analysis to get the timing information of what was going on here. It's a spike in temperature. What happened? Well, let me just summarize what is believed to have happened here. It's believed that there was a natural release of 1 or 2 or maybe 5 or 7 trillion tons of carbon over a fairly short time, only a few thousand years. And they've got that timing thanks to the Fourier analysis of the data that they can measure in this rock. You can see the sort of stripiness in the rock. That's a great big rock sample. You can see it goes black, white, black, white, black, white. And that's caused by solar effects, orbital effects. Okay, what happened? There was a release of 1 or 2 trillion tons of carbon. That was a natural release of some sort, methane or something coming out in massive quantities. They know that because of a carbon isotope excursion. So the ratio of carbon-12 to carbon-13 changes globally in the whole planet during this release. What then happened? Well, there was something like a 6 degrees global temperature rise. There were mass extinctions in some groups of species, and it took about 120,000 years for the carbon to then be removed by natural processes. So that's the experiment. It has been done. If you pull this trigger, if we say, let's release a trillion tons of carbon, what can go wrong? Well, it was a slightly different planet, so we can't necessarily generalize from this, but what happened on that planet was you got 6 degrees of global warming, mass extinctions, and it took hundreds of thousands of years for the system to recover. All right, so time is there. So let me very quickly say, what next? Why does this matter? That all sounds interesting. Well, maybe it's important. Where are we going now? Left-hand graph in blue is showing a smooth global temperature. We've had about 1 degree of warming since 1880. That's shown in red on the right in the context of the last 10,000 years or so. So it's a fairly unprecedented global rise in temperature. And the advice from climate science is that what really matters is cumulative emissions. Global warming, as a measure of climate change, is expected to be roughly proportional to cumulative carbon emissions. So it's not a question of reducing the emission rate by 10%, 50%, 80%. Actually, if you want to cap climate change on the vertical axis, you need to cap cumulative emissions, which means that the emissions rate has to drop to 0. That's an inconvenient truth. The slope of this roughly straight line relationship is not known. It's one of the most important unknown parameters. It's called the climate sensitivity, and the pink sausage shows the uncertainty of that slope. But whatever the slope, you still have the same message. If you want to stop the vertical thing, you've got to reduce emissions to 0 at some point. Okay, so that's an important message. And finally, there are some people who say, oh, who cares about 3 degrees of warming? This is a projection looking at the last 20,000 years and looking to the future of what we could be doing to ourselves by 2100. We could have 3 degrees of warming quite easily, maybe 6 degrees by the end of the century. Well, who cares? 3 degrees, that doesn't sound very much, does it? Well, hang on. That is the difference between the present day and the last ice age. So a 3-degree global temperature increase is a big deal. And just to put it in European terms, since that's where many of us live, let me finally show you some Met Office graphs, which they published in the last year. These graphs compare what's going to happen in Europe, what European summer temperatures will look like if you carry on along this sort of business-as-usual curve in red, with emissions getting bigger and bigger every year, or if you manage to get on this absolutely heroic dark blue line where the emissions rate is reduced to 0 by the end of the century. You might remember that the summer of 2003 was a record-breaking summer. It was the hottest summer ever recorded in Europe. There were heat waves and droughts, and people died. So something you could ask is, according to these climate simulations that the Met Office does with their supercomputers, how frequent are rare events like that going to be? This was the hottest summer ever, so an extremely rare event. How common will that be? Right, here's 2003. That's the hottest summer ever. The black line is the historical curve. This is showing average European temperature in that map area in June, July, and August. All right, so there's the record with the mouse on it. And the blue line shows lots of simulations of the future. And you can see that by 2050, that record will be broken 50% of the time. So half of all summers, even on this super-duper heroic blue line with the climate change action, half of all summers will be hotter than the hottest summer ever in 2050, and that's in our lifetime for most of us. Whereas if we don't bother taking any climate change action at all, on the red line, 99% of all summers in 2050, in your lifetime, in the lifetime of your children, will be hotter than the hottest summer ever. I think this matters. So I'm done. I want to tell you, act. Let's do something, okay? And if you want me to be more explicit, what do I mean by act? Society needs to assess uncertainty, assess its options, assess costs, damages, use decision theory and game theory to choose sensible actions. And I think that's the sort of thing people in this room are good at. Thank you for listening.
So before the coffee break, do we have any questions?
Presentation, and we have heard a lot of things about we must take action to battle this global warming. And I think maybe you as a professor must know a lot of people from the industry and from the politics, and what are their current attitude, and are they actually taking any actions or planning to take actions?
Okay, so the question is, what actions are people taking, and what actions should we take? That would be the topic for about 9 hours more talk. So I'd like to mention that there is a tool for the UK describing all the options, all the levers that the UK could pull on. It's called the 2050 calculator, and it allows you to explore which actions do make a difference and how to make combinations of actions that add up. And recently, the same team that made the 2050 calculator for the UK led the project to make a global calculator, which describes all the levers for the world. And I've actually got that here in my browser. No, I haven't. Where has it gone? That's Thompson sampling. Okay. All right, here it is. And it's just incredible how important some levers are that people haven't been paying much attention to. So how about diet? You know, we hear about nuclear power. So that's a contentious thing, and there are people who say, yeah, nuclear is important. And yep, you can crank nuclear up and down, and it makes a bit of a difference to cumulative emissions. So fair enough. But what about diet? If we get everyone to live on vegetarian diets, see the effect that had? The grey bar there is the cumulative emissions by 2100. And so just going from a sort of let's all live like Europeans, or something slightly more restrained, to let's all live not completely vegetarian, but mainly vegetarian, that has an absolutely massive effect. So that's not an action that people are talking about at the moment. I think all these things need to be discussed. There was another question at the back.
You were talking about this mass release of carbon of like 6 trillion tons of carbon.
Yeah.
If we add up the cumulative emissions from 18 whatever, how far are we?
Yes, the cumulative emissions, it's not known exactly how much were released in the PETM, but 1 or 2 or 6 trillion tons is a rough estimate. And where are we on this graph? This is 1 trillion tons of carbon here. That would be 2 trillion tons. So we haven't reached 1 trillion tons yet. It's quite credible by the end of this century or a little bit later that we might get to 2 trillion tons if humanity doesn't turn itself around. We're sort of halfway. We've used up half of the budget. And that's mainly fossil fuels, but it's also cement and land use change. Deforestation is causing the carbon release. So we've used up half of this budget if you view 1 trillion tons as the budget. I'm not saying we should view it, but a lot of people do talk about 1 trillion tons as being the sort of indicative budget beyond which you don't want to go. Of course, it depends on the climate sensitivity and what you think about the losses and the damages, where you want to set the limit. But we're sort of halfway to 1 trillion tons.
Okay, then let's thank David again for a very entertaining talk.